Okay, we are still in section 2.6, limits at infinity, and we're on example 21 at this point. So we want to evaluate the following limits, and these are some actually famous functions, and I want you to understand now that you understand how to do limits at infinity, how do you find the limit of these guys, or how would you find any horizontal asymptotes these might have. So the first one is just sine of 1 over x. So how can I evaluate that? Well, first of all, remember that we learned that if sine is a continuous function, and sine is continuous everywhere, we can move the limit inside. So I'm going to take, this is the same thing as the sine of the limit as x approaches infinity of 1 over x. So that's now a simple limit. As x gets really, really big, 1 over a huge, huge number gets closer and closer to 0. So this limit is 0, so I'm actually wanting the sine of 0, which we know is 0. So this limit is equal to 0. Now in this example, we're going to have some other indeterminate type forms pop up, which you haven't seen yet. So, and I wouldn't expect you to actually be able to handle this one on your own yet, but I want you to see how this works. So the limit as x approaches infinity of x times the sine of 1 over x. So as x goes to infinity, x itself goes to infinity, and then times the sine of 1 over x we just learned goes to 0. So infinity times 0, that's actually not a number. You can't say that that's like 1 times 0, which is 0, or 5 times 0, which is 0, because that's unimaginably big times unimaginably small, right? These are limits. So infinity times 0 is indeterminate. Remember what that means? It means we cannot yet determine what the answer is, so we have to do something. In this case, it's really a change of variables trick here. If we let t equal 1 over x, then this 1 over x would become sine of t, but then what does x become? Well, just solve this for x, I get that x equals 1 over t. So we have 1 over t. Now, what happens as x goes to infinity? Then as x goes to infinity, what happens to t? T goes to 1 over a huge, huge number, which is 0. So we have the limit as t approaches 0, in this case from the right, because this is, we know this is positive since x is going to positive infinity. So as the limit as t approaches 0 from the right of 1 over t times sine of t, but notice that's sine of t over t. And that's our famous limit. That's like the limit as theta goes to 0 of sine theta over theta. We know that that guy is equal to 1. And if you were to graph x times the sine over 1 over x, it has this rapidly oscillating stuff going on close when x is close to 0, and then it has an asymptote approaching y equals 1 as x gets closer and closer to infinity. Okay, so that's that one. This next one's pretty simple to evaluate, but it's just an interesting function that we use all the time. It's a dying out oscillation. So the limit as x approaches infinity of 2 plus sine x over x. So I have a sum of two functions. So I can take the limit of the first guy, limit as x approaches infinity of 2. The limit of a constant is just that constant 2. And then sine x over x as x approaches infinity. Well, we know sine of x stays between 1 and minus 1 forever. It oscillates between 1 and minus 1. So as x itself gets bigger and bigger, some number between 1 and minus 1 divided by a huge, huge, huge number gets closer and closer to 0. So this becomes 2 plus 0 equals 2. So the limit of that guy is 2. It has an asymptote at 2. And the last part of this example, part D, is another situation where I have an infinity minus infinity, the indeterminate form. And you haven't seen this type of indeterminate form. That's another indeterminate form. So notice if I plug in x, as x goes to infinity, this guy goes to infinity, minus infinity, square root of infinity is still infinity, so this goes to infinity. So infinity minus infinity. You cannot say that that's 0. You have to, it actually works out to be 0 in this case, but you can't say that initially, because this infinity could be bigger than this infinity or vice versa. So you can't say yet what that is. So that's what we call indeterminate, yet to be determined. So how do I do that? The trick here is to multiply by the conjugate. In other words, change this sign to a plus and multiply it by that. It allows you to get rid of the square root in the numerator when you do that. Because notice when you FOIL these guys, you get x times x is x squared. Then you get minus x squared, square root of x squared plus 16 times x, and plus square root of x squared plus 16 times x. Those cancel out. Then you have minus square root of x squared plus 16 squared, so that's just minus x squared plus 16, the quantity. Now, you can't change the problem, so what you have to do is you have to also divide by that conjugate, x plus square root of x squared plus 16. So that stays there. You can't do any simplification. But what happens? In the numerator, the x squared minus x squared cancel, and I'm left with just minus 16, right? I have to multiply above and below by the highest power of x I see, either the x here or the square root of x squared, which is also x. So 1 over x, 1 over x. This becomes minus 16 over x. As x goes to infinity, that goes to 0. Above and below, multiplying by 1 over x, that's the same thing as multiplying by 1 over the square root of x squared. So that brings in x squared inside the denominator. So x squared over x squared, 16 over x squared, 1 plus 0 as x goes to infinity. So 0 over 2, and it's 0. So again, that's a semi-complicated thing. You do have a homework problem or two where you need to do that though. So just multiply by the conjugate and then evaluate it like you would all rational functions.